Hi, everyone. Okay, we can get us started. I'm Samaya Kakbash. I'm a Callis Fellow at Rutgers University and a coordinator of the Microlensing subgroup of TVS. And today, Katarzyna Kruszyńska, Natasha Abrams, and me are chairing this session. Thank you so much for joining us. So, well, it's the last day. We've already seen these slides many times, but I want everyone to please be aware of the code of conduct. And if you experience or witness any violation of the code of conduct, please contact any of the persons mentioned here on this slide. And also, please be conscious of the name tags and the stickers on the name tags and the way people would like to be greeted. And also be please conscious of the social batteries of people. It's the last day. And then finally, okay. So yeah, so for the participants online, please make sure you're muted while the talks are going on. And if you have a question, you can unmute and ask your question, or you can leave the questions. We prefer to leave the questions on a Slack rather than the chat because it's harder to see, but please let us know if you have any questions. And all right, so we're going to start. We're going to have 5 talks, and after that, we're going to have a hands-on session in which we're going to work on software for microlensing detection and classification, the work that has been already started as part of a sprint week a few weeks ago. And we're going to continue to work on that more closely with broker representatives and other people who are interested in the sort of like software we're trying to develop. Okay, so we're going to have our first speaker. I don't see I can see the cursor here. Oh, yeah. Yeah, that's. Yeah, thank you. Our first speaker is Katarzyna Kruszyńska, who is a researcher at Las Cumbres Observatory. Katarzyna?
Thank you for introducing me, Samaya. Hello, everyone. I'm Katarzyna Kruszyńska. I'm a postdoc at Las Cumbres Observatory working with Rachel Street. And today I would like to, today I would like to talk to you about a little bit about all of the activities me and my collaborators have done in preparation for the first gravitational microlensing events from Ruben. Okay, so I am the first person talking about microlensing in this session. So here's a short reminder for people who may be not as familiar as most of our group. Microlensing is an effect of Einstein's general relativity. It happens when we have a massive object, the lens, it will distort the space-time around it. And if the lens is moving between crossing the line of sight between the observer and the distant source, the light of the source is not following through the straight line anymore. It's bent, and the apparent position shifts. What microlensing does, it splits the image of the source into 2 unequally magnified images, which then create a characteristic bell-shaped light curve that appears when the source lens and the observer move in and out of the near perfect alignment. I have added 2 beautiful videos that you can click on if you download this PDF, and it should explain better what I was trying to explain to you. But since I am So this is very short. I will just hop into why we care about microlensing from Rubin. Because Rubin will probe hidden populations which are not accessible to current surveys. Rubin has an unprecedented depth and width in covering the galactic plane, and it has a it has a great ability to detect these rare phenomenons. Because of that, Rubin has a capability to, microlensing is a very rare phenomenon because it requires this near perfect alignment of source lens and the observer, but Rubin is predicted to detect even up to 10,000 such events per year. However, Rubin cadence is relatively moderate in the galactic plane, but that still means it's a perfect discovery engine for moderate and long duration events, which are connected to objects such as the remnants of dark stellar evolution, such as black holes. However, and also, like, Rubin has now this augmented cadence, one season of augmented cadence in the galactic plane and the galactic bulge specifically. So this drives this even more. However, there are two challenges that Rubin will have with microlensing. First of all, these are rare phenomenon. You get only like a handful per night if you're lucky. These will be buried in millions of transients detected each night by Rubin. So we have to dig them out from the alert stream. Second of all, even though Rubin is the perfect discovery engine, it will Rubin's photometry will not be enough to fully characterize these events and find out what is the cause of what is causing this microlensing event. However, we have things called target observation managers, which are designed to alleviate those effects. So a target observation manager is a platform that exists in this large system that I have shown here. Basically, it aggregates the information coming from alert brokers or from other surveys, swallows them up, and then it can prioritize targets and can select targets, classify them, and request follow-up observation with other facilities. And this whole thing, if it works correctly, and we are working on that, will help us find those amazing black hole events or other objects. For Rubin microlensing specifically, there are two such platforms currently being designed or working. First of them is the MOP, microlensing observing platform, and second one
So I jumped to the other two rooms. All three Zooms are out. I think they're being worked on now. Maybe I'll go get a load of laundry started.
For alert brokers, I think they don't, they are not, they do not take coordinates into account. What they're looking at is like light curve features. So in principle, we are still able to, we will still be able to detect microlensing events from Magellanic clouds. How it looks like, I'm not sure. I think the current effort from the microlensing group was to focus on the galactic plane science.
What is the minimum number of observations which are inconsistent with constant flux that you need to think you might have a microlensing event?
Oh, that is a fantastic question.
I've been doing this for a while.
Yeah. Wow. I am not sure. We usually, Rachel, do you have a number? Is it 3?
There was a study by Daniel Godinez who tried out a detection algorithm, machine learning based random forest classifier. And he tried it specifically on relatively low cadence data similar to Rubin. And he found that a baseline of typically 1 year was required to rule out almost all false positives for microlensing. There's a few that remain, things like dwarf novae can still fool us, but most of them are ruled out with a year's baseline.
Ish.
Yes, provided it is showing roughly the same amplitude in most passbands, because for us, yeah, exactly.
Yep.
For microlensing, that's one of the distinguished. Not necessarily. It depends on the timescale of your microlensing event, and we're looking at quite a wide range of timescales. Yes. No. I misunderstood what your question.
Could someone in the room please repeat the comment into a microphone?
Oh, sorry.
I apologize. Usually this suffices. So you tell us, how many observations you need whether in a single filter or multiple filters in order to establish. And I understand that you need a year for a baseline, fine. But after that 1 year baseline, how many observations do you need?
Yep.
Okay.
Yep.
Thank you.
That being said, that like we have to constantly reclassify our target
Can people online please confirm if they hear us?
And, oh, yes, somebody. Thank you, Gary.
Just came back on.
Perfect. Okay, well, sorry for that hiatus. And I'm getting an echo. Okay, let's try that. Nope, that is muted. That's the wrong talk.
Oh.
We did that one. Yeah.
Yeah.
Okay. That's the speaking. Ah, hey, great.
Okay, now
Perfect.
hear and see.
Okay, if the folks on Zoom could kindly confirm that you can hear one more time.
Yes.
Woohoo! Okay, let's make hay while the sun shines, as they say. Well, sorry about the interruption, folks. Apparently the hotel's network connection went down at a very inopportune time. So my name is Rachel Street, and hello, everybody. Thank you for the opportunity to speak. I would like to talk about the scientific return we can get from enhancing the data we'll get from the Rubin survey with that work from the Roman mission, which will be operating contemporaneously. The work that I'm about to describe is obviously the work of many, many people. In particular, I would like to acknowledge the TVS Microlensing group, who are super active. And in addition, from the Roman meeting, there's the Galactic Bulge Survey Project Investigation Team and the design committee from the Galactic Plane Survey. So first of all, let's look at how these surveys will complement one another. Starting with the familiar, this is an outline of Rubin's Galactic Plane Survey footprint, just as a reference point to compare with later plots. Assuming that science operations begin as planned, then the first earliest observations we get within this footprint should be around about February next year. Now, as we've heard earlier in this week, the cadence that LSST will deliver is somewhat complex. Following the recommendations from the TVS Microlensing group, most of Rubin's footprint in the galactic plane will receive very regular cadence over the full 10 years of the survey, primarily focusing on GRI and Z filters. They will take data in U and Y, just not as frequently. In addition, a single Rubin pointing within the central galactic bulge will receive augmented cadence, again mostly in GRIZ, and typically will receive around 160 visits per year, starting probably in about year 3 onwards. It's worth mentioning that there is still scope for optimizing the exact pointing of that chosen field. Moving on to Roman, the mission is on track to launch in October 2026. The majority of the time, although not all, is dedicated to 4 core community surveys. Of these, 2 are particularly relevant to microlensing, so I'll focus on those. The first up, which I'm sure most people here are familiar with, is the Galactic Bulge Time Domain Survey. This was actually one of the core mission drivers. So this aspect of the mission was custom designed to characterize microlensing events across a range of timescales from free-floating planets right through until compact object lenses. It has an interesting cadence as well. It will perform 6 seasons of 70.5 days of very intensive observations of 6 fields in the galactic plane. Those observing seasons will be tightly constrained by the visibility from the spacecraft, and they'll be timed to happen in the first 3 years and last 3 seasons of the nominal mission. It will make a visit to each field in the pointing roughly once every 12 minutes, mostly making observations in the wide passband 146 filter, but also doing regular observations about every 12 hours in both redder and bluer filters in order to get time domain color information on all stars in the field. There will also be, we discovered recently, some lower cadence observations roughly every 3 days during the off seasons to provide continuity for the microlensing events. This is actually a survey overguide, meaning that this is actually more than we nominally asked for from the pit. So that's great news for microlensing. And one of the changes that were made was an additional footprint in the galactic center. More recently, the Roman survey has added a community survey in the wider galactic plane in response to community requests. This survey was allocated at the start a maximum of 700 hours and constrained to execute those observations within the first 2 years of the survey. There was a number of opportunities for the wider community to put in white papers and science pitches to recommend what should be done with that 700 hours. And the design committee is very grateful for all of the input that they received, including a number of contributions from people here. So thank you. Oops. The full report on the design of the Galactic Plane Survey is due out very shortly, I promise. But here is a sneak preview of what's going to be included. Most of the time is going to be dedicated to a wide area survey of the whole of most of the galactic plane, and including an extended region of the galactic bulge, which is shown in the white outline on this plot. This will take place in 2 epochs in order to provide proper motion measurements for as many stars as possible, and it will be covered in 4 filters in total. There will also be 6 specific pointings, which are outlined in blue, for which time domain observations will be made. Now, obviously, we can't do a huge extensive time series with just 700 hours, but there will be time domain observations for those particular pointings. And 2 of these cover a large area of the galactic center at high cadence, but also extending over a few weeks. There'll also be 15 fields for which we'll get deep multiband and spectroscopic data over a range of targets that were recommended by the community. So I'd like to take a quick look at how these data sets will complement one another. First of all, the bulge will obviously cover a small footprint, but at very high cadence. And over those 70-day seasons, there's limited amounts of microlensing light curve that you can cover in that period of time, as illustrated in this simulation by Annabelle Varela. Rubin's longer but regular cadence will help to fill in that gaps and catch anomalies that would otherwise never be seen. Roman's high precision astrometry will also provide additional constraints on the microlensing parameters. This is a quick illustration about how those cadence observations might complement one another for the galactic center field, taking into account the various different visibility windows of that region for different telescopes. I realize I'm tight on time, so I will move forward quickly. Of course, Roman and Rubin span quite complementary wavelengths, and they will span together quite a wide range of wavelengths in the optical and infrared, which is ideal for characterizing and identifying a wide range of stellar variability. Now that has intrinsic value, of course, but it's also vital for us to help rule out false positives, identify microlensing events, and also to characterize microlensing source stars. The advantage of observing without an atmosphere is that Roman will get some beautiful spatial resolution, as shown in the simulated image produced by Matthew Penny. That will be enormously helpful to help us deblend the more crowded Rubin images at these extreme depths. A microlensing analysis is extremely sensitive to extinction and reddening, which is very, very complex in these field of views. And so the combination of Roman and Rubin observations will be able to map the extinction to greater depth and greater detail than before. Now, I don't have time to go into all of the amazing science that we're going to do with both of these surveys combined, but I hope I've given you a flavor of the ways in which that they can complement one another. We do have some work still to do. There are still a few optimizations that we can make. For example, the exact pointing of the augmented region of Rubin observations in the galactic bulge. And we're working with the Roman Time Allocation Committee in order to maximize the science return from both surveys. And I will stop there and take questions. Thank you.
Thank you so much, Rach. We have time for one question.
Perhaps since we were late starting, maybe we should move on with the agenda.
Yeah. Thank you. Thank you so much again. Can you please applaud? Our next speaker is Natasha Abrams from Berkeley.
Hi, everyone. My name is Natasha Abrams. I'm a rising fifth-year grad student at UC Berkeley, working with Jessica Liu. And today I'll be talking about searching for black hole microlensing with Rubin. So we got a great introduction from Katarzyna about microlensing in general, but I want to start by iterating that we can actually start to infer the mass of the lensing object with photometry alone. And that can be done with two different quantities. One is with the Einstein crossing time, or TE, which you can think of like the duration of the microlensing event. TE, the duration, scales with the square root of the mass of the lens. There's also the microlensing parallax, or pi-e, which is when over the course of the year, as the Earth goes around the sun, you're viewing the microlensing event from different angles. And so you can see bumps and asymmetries in the light curve. And that scales inversely with the square root of the mass of the lens. So you can see here, we have the microlensing parallax as a function of the Einstein crossing time for a set of simulated microlensing events, where in blue we have the stars, in orange the white dwarfs, in green the neutron stars, and in red the black holes. And you can see that in this parameter space, the black holes start to separate from the rest of the population because of their large mass. However, you can't just look at a single microlensing event with photometry alone and say, well, this is a black hole, because there's other things such as the relative proper motion between the lens and source and the relative parallax between the lens and source, which cause dispersion in the space. We can do better though. We can look at the astrometric microlensing signal. This is the positional shift that's on top of the photometric shift that you see when the lens passes in front of the source. So in this animation, we are in the frame of the lens. In orange, you have the lens, with the red open circle is the source, and the two blue images are the distorted images of that distant source. Because we can't actually resolve those images, instead, we see the filled in red circle, which is the apparent position of the source. The difference between the filled in red circle and the open red circle is the astrometric shift that you see in a microlensing event. The maximum astrometric shift is directly related to a quantity called the Einstein radius, which along with the microlensing parallax that can be gleaned from the photometry, you can just measure the mass of the lens and determine if it's a black hole. So this technique was used to discover the first isolated stellar mass black hole. So here you can see this background source get brighter and fainter again as the black hole passes in front of it. And here you can see the astrometric shift that's measured. In gray is the unlensed background star if it weren't being lensed, and red is the actual path that it took when the black hole passed in front of it. So Rubin alone can't do these astrometric measurements. You need to actually alert on the photometry and follow it up with other facilities such as Hubble, Keck, James Webb. And so I wanted to go through some considerations when alerting on black holes with Rubin to follow them up with other facilities. So one thing is that you may need more than 1 year of data. A standard alert packet comes with the 1 year of data. However, this is actually the case for all microlensing events, as Rach was mentioning earlier, that we really require at least a year of baseline to establish that it wasn't variable before, which is one of the easiest ways to tell that it's not microlensing. And however, though, for black holes specifically, since you have a long Einstein crossing time, you could be alerted in one season, and the bulk of the microlensing event could be in a separate season. And so that's one thing to consider when alerting on these. And so potentially through Workers, if we were able to access a longer Rubin baseline or to match against other services like ZTF, it would help get a kickstart for alerting microlensing in general and black holes specifically. Also, modeling including microlensing parallax is important to select good candidates, since just looking at the duration of the event isn't enough to tell that it's a good black hole candidate. You also want to know that it has small microlensing parallax. And so that's something we're looking into doing with Antares. And so something that's still to be considered is the need of multiband photometry in the alert process itself and how that would be combined. And so as Katarzyna talked a lot earlier, using a TOM or Mintleaf, which is another similar platform built on SkyPortal, which aggregates the alerts where in the broker stage, it's determined whether it's microlensing, and then it's aggregated together to determine if it's a good candidate for follow-up resources. And so beyond looking astrometrically to determine, well, this is a black hole, we can also start to statistically constrain the black hole population with photometry alone. We can look at the population and say, this is the black hole mass function, potentially in different parts of the galaxy. However, this is based on galactic models. And so we have the microlensing parallax as a function of Einstein crossing time plotted here again, and the exact distribution of these things, where if you were to plot a lens posterior, so the posterior of if you fit the microlensing event, the exact positions of these populations are dependent on the galactic model, the velocity distribution, the spatial distribution. And so modeling that well and taking that into account is important for making good, being able to say, oh, this is the black hole mass distribution and stuff like this. And so we're currently running galactic simulations to do this. I'm working with an UC Berkeley undergrad, Sadra Mula, to run a code called Popsicle, which is a microlensing population synthesis code with Rubin parameters. So he's incorporated Rubin filters by creating a transformation from UBB filters using a numerical grid. And we're going to simulate an array of fields across the galaxy to both understand the sensitivity to microlensing events in these different places, but also to understand the different distributions as the velocity distribution and spatial distributions change throughout the bulge, the measured microlensing Einstein crossing time distributions and parallax distributions also change. Another great thing about Popsicle is that we include the blending of the nearby neighbors. So not only are you going to get a distribution based on the galactic model of the of the source star magnitudes, we're also blending it together with the neighboring stars. So this is something that we've brought up as a like science group a number of times. It's getting color dependent blend, and that's incorporated in this. So in summary, Rubin will both discover black hole microlensing that we can trigger to do follow-up astrometrically and statistically with photometric only galactic models. However, there's still a lot of work to be done to get there. Thank you.
Thank you, Natasha. Any questions? There's one on Zoom, but I can't see it.
There is one question on Zoom from Charles Liu. Would the value of multi-band photometry primarily be confirming it's a microlensing because lensing is independent of wavelength?
Yes, so this would be one major way that it could be helpful. Another way that it could be helpful is that just in the cadence of Rubin, being able to incorporate the all of the different bands essentially gives you more coverage over the whole event. Another chat. Okay.
Thank you. Are there,
So the simulation you mentioned at the end with Popsicle,
Mhm.
that's over at the section in the galactic bulge, which is obviously where most of the microlensing events are. I realize that to extend that out to across the plane would be a significant challenge, but it is something that we have spoken with the folks nearby in Berkeley who happen to have a supercomputer. So is there any traction on rolling this out on a larger scale?
Yeah, so we're using the resources at NERSC, a supercomputer that's at the Lawrence Berkeley Lab, to attempt to simulate across the galactic plane.
Cool.
Thank you so much. Let's thank Natasha once again. Our our next speaker is on Zoom.
Hello.
Hello.
I'm going to-
Just one moment. Yes. So our next speaker, Karen Novogorovsky. I hope
Yeah.
I pronounced it correctly. Karen, can you share your screen, please?
Yes. Give me a second. Okay. Well, hello everyone. I'm Karen Novorovsky, and I've been working on this with the TPS microlensing subgroup. The work is about injecting microlensing events, microlensing Lycos simulations with RIN data preview. The goal is to create a flexible tool to inject and extract Lycos into DP0 at first, and now it works on DP1. It has a few possible applications like testing microlensing recovery, testing classification, and one example of application that we want to do is to assess the recoverability of microlensing light course as a function of image properties and more. This is just an example. Well, the pipeline, it has 3 steps or 2 steps. The first step is to simulate the microlensing light curve, where we use GenuLens to simulate microlensing parameters, realistic microlensing parameters, realistic stellar distribution with trilegal, and then we apply PyLima to simulate the microlensing light curves. So with this pipeline, we can simulate different type of microlensing models and system types. Then the image-based light curve simulator for LSST consists on inject any ideal light curve that you have. In our case, we use the microlensing light curves to the images from DP0 or DP1. then we use force photometry task to obtain the realistic LSST light course. And then you can apply this to every possible application. In our case, the parameters recovery will be the first one, or you can train variability classifiers and more. So to summarize, you can simulate a diversity of microlensing light cores. You also can recover light cores with data preview of any ideal light core. And you also can add cadence and noise, not by injecting and extracting the light cores, but using Rubin and a selected opsim. Here you can see how the code inject and extract the light core on one calypse with the source on one calypse. But the pipeline does do this on it first collect all of the calypse from one region to inject a lot of light cores in that region, and then inject and then run force photometry on each one. Well, this code was recently improved with modularization, parallelization, and documentation, and it will hopefully available the first version, so I can share the catalogs and the code to apply it to microlensing or your own light course. Then I have some examples of the light cores injected. Here's one example for DP0. It's a binary star. Here you can see the field of view of the injected calypse. And here you can see also the parameters of the light core injected and the magnitudes of the nearest source of the injected light core. Here we remove all of the flags points in injection flags or measurement flags, and we take into account the magnitude limits. Then for DP1, we choose to inject in extended Chandra deep field south in the center, just because of these fields have the most visits. Here's one example on an empty field, so it works well. It also works with a nearby source and also with a nearby spike. We also choose to inject on 47 Tucano because it has a very high stellar density, so we can understand the blending and the parameter recoverability on this gradient of stellar density that we choose. Also, we saw some features of the calypse in this region that we need to flag and not inject on them. This is the very recent. And just to summarize, the next steps are to assess how well the microlensing events can be identified by comparing the classification performance or running statistical tests for deviation from the constant. Also, we want to evaluate how accurately the microlensing parameters can be recovered using PyLima fitting. And of course, when the pipeline is ready, share the code for you and use it for further applications. And that's it. Thank you.
Thank you so much, Karen. Are there any questions for Karen?
Hi, Karen. Wonderful talk. I'm very excited that this is moving forward. Could you expand more about the problems you saw in 47 Tuk with calypse?
Yeah, I put some of the examples here. Well, it seems like there was some movements or problems with the tracking, I think. because of the horizontal lines that we can see in the first calyps. And well, also the stars are clearly not with a bad focus. I don't know which is the problem here, but I'm just thinking out loud. And also in the last calyps, we see that there's this happened in a few calyps. There's some black spaces without sources. I suppose that they couldn't done photometry there. I need to check if this is close to the center. I think that it is not. But here you can see that there are some holes. No, but the holes are just because there is not many sources there. No, I have not clear why are these features here.
Karen, if I may jump in there, and I see a comment from Will Clarkson in the chat saying much the same thing. According to the data management team, those horizontal lines are the result of a masking algorithm covering either a dead column or the column from a bright star. So this is something I understand that they are still working on.
Okay, great. Great to know it.
Karen again, thank you so much.
Thank you.
All right, so we're moving on into the second part, which is going to be the hands-on session, starting with a talk that will be basically updates on results of the sprint week that we had a few weeks ago that I'm going to present. And then after that, unfortunately, I have to leave earlier because I have a flight to catch, but Katarzyna and Natasha are here and they will tell you more details of how the hands-on session is going to basically initiate and then how the wrap-up at the end will be. So a few weeks ago, we had this sprint week, which took, it was like a daily session for 2 hours for 1 week, in which we created different groups. And we started to work on software that we needed for detection and classification of the microlensing events for Rubin. So here I'm showing you these 5 main groups. Within each of these 5 groups, there are like smaller tasks that people are individually working on or within a smaller groups. So group 1 was focusing on the Antares broker. We have been working on developing a filter for the Antares to detect and classify microlensing. One thing we have tried to basically implement was to implement different detection and classification methods for each of these brokers so that we can basically evaluate their performance and see what they do. And group 2 has been focused on the Think broker and the software for the Think broker. Group 3 has been focused on improving the simulations that we already have and the classification methods from different groups. And group 4 has been working on the Ample broker that we have recently basically started to interact with and learn about. And group 5 has been like even before the sprint week for a long time ago as part of an in-kind contribution project have been working on infrastructure needed for the Microlensing Science and which could be also used for other groups. And then today we're going to also start working on the Alerce broker and basically try to interact with it and learn how we can basically get the alerts and sit down and try to look at the microlensing candidates from Alerce and see basically what we need in order to be able to get the data and start working on it. So the next slides are basically updates on each of these groups. And there's a lot of information on those slides, and I'm not going to go into in more detail, but those slides are going to be online, so you can refer to them. And if you're interested in any of those works, you can contact those groups, and you can stay here and work with those groups on those projects. But I'm just going to very quickly go through these slides. So this is basically the filter we're developing for the Antares. We're looking at the features in the alert package in Antares to see which ones can help us basically set some cuts and narrow down the sample we want to fit. We are also basically using our experience from other surveys like ZTF and the metrics that we have used for those surveys and implement them here. We're also using a detection algorithm that was initially implemented by the KMTNet survey, which is a microlensing focused survey, and we're testing that on Rubin. We actually did test that detection algorithm on DP1, and the events that passed our metric were events that we could definitely not basically confirm as microlensing candidates, mainly because we don't have enough baseline. And that's one of the main things that we need in order to be able to confirm these events. And also, like, the sampling in some of the fills were not suitable for microlensing. And then we also learned that we need better pre-filtering cuts to basically to narrow down the sample we're feeding with our detection algorithm. And then this is a work being done for basically implementing a detection and characterization algorithm for ample broker, which you can take a look at. And then there's also the observation manager, the observation program management. Is that the OPM? Yeah, yeah, OPM. Yeah, so this is a platform where we're going to receive the alerts, and these alerts are going to be basically processed and prioritized for follow-up. There will be like filters, classifiers, and cross-match with catalogs. And this is part of the in-kind contribution program that Marcus and Yanis are leading. And then we're also working on improving the simulations. For example, adding more categories like B stars that could be basically mistaken for microlensing to enhance our simulations. And then we're also, we have classification algorithms like Microlia, which has been implemented for the Think broker. And we have this group within the Sprint Week that is working specifically on enhancing this classifier to detect not only microlensing events, but to classify different types of lensing. And then there's also, we have multiple teams focused on improving the existing plastic elastic data sets by adding more microlensing events, more categories of light curves. And if you're interested in adding your own kind of like other categories that you're interested in, please contact people who are involved in this group. And this is also the same. So that's the end of the updates. Thank you so much. And so we're going to move on into the hands-on session, and I'm going to ask that Natasha, you can just give us instructions. Thank you.
Yeah, first, thanks to all the speakers again for the session. Cool. Okay, so now the way that we have it set it up is we have breakout rooms for each of the different brokers. And you're invited to join the one. So we have also help from a few of the different brokers, mostly online, a little bit in person. And so we invite you to join the relevant breakout session. They should be labeled by the different, they should be labeled by each of the different brokers. So what's it called? There's an Antares one, an Alersi one, a Fink one, an Ample one, and just other for any other catch-all thing that we didn't come up with. If you haven't, so the Antares one is going to be more, as Samaya said, a little bit more traditional, like with like fitting and yeah, that sort of traditional method. Alercy is, we're just starting the collaboration now. So if you haven't joined one before and you would like to, that might be a good place to go. Think is going to be a little bit more on the machine learning side, and so is Ample. So we're going to attempt to get the Zoom stuff to all be working, and we invite you to join those. Thanks.